Let's look further at the way in which mathematics, some of it quite advanced, has enabled the scientists to understand the structure of the honeycomb. Some 2.5 centuries ago, a French astronomer, Maraldi, became fascinated with bees. One thing he noted about the double rank of cells in honeycomb is that their bottoms are not flat, but convex, formed of 3 rhombi. Obviously, the obtuse angles where bottom meets wall make it easier for the bees to construct the cells and to keep them clean. But Maraldi noted that there was a remarkable constancy to the angles of the rhombi. They measured about 70 degrees. He suggested that the bees had used this angle for the sake of simplicity. For if the acute angles of the rhombi are 70 degrees 32 minutes, the angles of the side trapezoids are identical. Réaumur, a noted French scientist, suspected that there was a further reason for the special shape. He wrote to a number of mathematicians asking what angle would give the most economical trihedral base on a hexagonal prism. Only one, Koenig, came up with an answer. To get his answer, he first proved that the volume of all hexagonal prisms with trihedral bases is the same, provided that the height h and the side A remain constant. This is easy to see. If a piece is cut off one place and put back on at another, the volume does not change. But as this distance changes, the shape of the prism and the area of its surface change. If this distance is called x, this is the formula for the surface area. It consists of the areas of the 6 rectangular sides, less the triangular pieces, plus the areas of the 3 rhombic ends, which can be calculated by means of the Pythagorean theorem. Substituting in this formula, calculating values for x equals 0, x equals 1/10, and so on, plotting these values, x equals 4/10, 6/10, and so on, and then connecting these points gives us a graph which shows that the area is at a minimum when x lies between 3/10 and 4/10. In other words, the prism with the flat base and the prism with the very pointed base have more surface area and would require more material to build than the intermediate one. Unfortunately, no amount of graphing or even brute force calculation will yield a mathematically precise answer. But there is an elegant shortcut to an exact answer. Some 300 years ago, Newton invented the calculus. About 75 years later, when few men understood the method, Koenig manipulated the formula for the area according to the precise rules of the calculus. The mathematician calls it differentiating with respect to x and equating to 0 to minimize. This process yields the precise point where the surface is at a minimum. With complete generality, this occurs when x equals a, the length of a side, times the square root of 2 divided by 4. The cell then has the shape the bee uses with the angles of the rhombi that Maraldi gave. Someone may wonder whether this is so economical. Isn't it necessary to waste wax to build 2-pointed ends? Bees have the answer to this. They build the cells so that the bottoms are offset. Each cell fits into the pocket formed by 3 cells on the opposite side. Modern science, with its high-speed computers and intricate formulas for stress analysis, has not been able to improve on the honeycomb. It has merely confirmed it as the ideal structural shape. But man could not understand the perfection of this pattern which the Creator had given to the honeybee until after he understood the mathematics involved. For as Galileo noted, that vast book which stands forever open before our eyes, I mean the universe, cannot be read until we have learnt the language. It is written in mathematical language, without which it is humanly impossible to comprehend the single word. This insistence on the importance of mathematics made Galileo the father of modern science, for this discovery is the very cornerstone of science. Today, continued scientific progress depends on a more thorough, a broader application of mathematical concepts. Thus, we can discover more of the order the Creator has built into the universe. Only thus can we read further in the great book of nature which lies open before us.